Hello, AP Calc BC students. Mr. Record here, and we are just about at the final stage of our journey through the convergence tests. We're looking at topic 10.8, and the way that I follow the curriculum at my school is I take care of 10.9 and 10.10 prior to this section. So this topic is actually the finale. This is the last of the convergence tests that you're going to learn from me, and I'm going to admit, it's my favorite test. I love this ratio test, and I think you might start to see why as we work through it. So let's go ahead and take a look at what this test is all about, the ratio test for convergence. So I jump right into it. Here is another test. So basically, you've got a summation a sub n. All right, well, what do we do with this? Well, it says the summation a sub n converges if you take the limit as n approaches infinity of the nth plus 1 term divided by the nth term's absolute value of that turns out to be less than 1. So it's similar to some things that you've done in previous tests where you find the limit of a ratio, but instead of using a compared to series like we did in the limit comparison test, you're actually using the nth plus 1 term, and we'll talk about how to get that term again here in a moment if you've forgotten. If by some chance you end up with a limit that has a value greater than 1, then your summation diverges. Now, keep in mind that getting a limit that's equivalent to infinity is the same as being bigger than 1. So it seems like there's one other possibility that we haven't taken into consideration. If by some chance that limit is going to give you an answer of 1, it just simply means that the ratio test is inconclusive. Now I'm going to tell you something. I don't know if you're going to see the third option happen very often because typically there's another test that would have probably caught your eye before you even thought about using the ratio test. I'm not saying that 3 will never happen, but in the unfortunate event that it does, it just means that you need to move on to another test. All right, well, let's go ahead and take a look at some examples. And that's really the purpose of this video, is to look at example 1, which has plenty of examples. You've got 4 of them here that we're going to look through. So here we go. First thing that you're going to do is you're going to write your limit statement. And then we're going to know that we're going to be taking the absolute value. Now, I think as time moves on, we'll talk about the role of this absolute values. I don't want to say that you can't use this ratio test for an alternating series. You certainly can. It seems like the alternating series test might be the most go-to test if you have an alternating series, but under certain circumstances, you might be able to pull off this. And that's kind of what these absolute values do. They will wipe away any alternator or alternating component. We'll talk about that later. So you're going to start by taking the nth plus 1 term, which is just simply all of these n's changing to n plus 1. Once you do that, you're going to divide by the original term, which is 2 to the nth over n factorial. And like I said, all of this is going to be inside these absolute values. All right, now what's going to happen after this is that we take this limit as n approaches infinity, and I start to look and think, really, do the absolute values serve much of a purpose? Do you see any situation where anything is going to be negative given the fact that n starts at 1? And the answer to that is no. So at this point, you can remove the absolute values. Again, I know you're probably thinking, well, why are they there? To be honest, the reason is going to be a little bit more clear when we move to the next unit. We start talking about power series and their convergence. So we're going to go ahead and multiply by the reciprocal. That's what you do when you have complex fractions. So the 2 to the n plus 1 on top is going to be joined by an n factorial. And then on the bottom, we have a 2 to the n that's joined by n plus 1 factorial. So hopefully that's making sense to everybody. At this point, you can go ahead and simplify. You're going to have to simplify, and this is sometimes the hardest part of the problem. knowing what algebra rules to use. 2 to the n plus 1 divided by 2 to the n. Well, whenever you have like bases, you know that you can just simply subtract those exponents. And 2 to the n plus 1 minus, or I'm sorry, n plus 1 minus n is just 2 to the first, and that would be located on top. Now, we've talked a little bit about these factorials before. N factorial on top, n plus 1 factorial on bottom. This n plus 1 factorial can basically be thought of as n plus 1 times n minus 1 times n minus 2. Well, that n all the way down is just nothing more than n factorial, which points the n factorials will cancel, and all you're left with is just a plain old n plus 1. Now apply your limit. Lots of different ways to do this. You could just think of it as, whoa, the denominator is getting big in a hurry. And that is true. You could probably also compare the degrees of the ends and see that this one's definitely bottom heavy. So that means that the limit's going to be 0, no matter how you do it. And then if you think about, if I have to go back, that's fine. Is that going to be condition 1 or 2? Well, 0 is definitely less than 1. So we have a convergent series on our hands. And that's really what the ratio test looks like. Now, the idea behind the ratio test is probably pretty easy to remember. You got to really keep tabs on the less than 1 versus the greater than 1 outcome. But what makes the ratio test sometimes challenging, at least at the beginning, is the wide array of expressions that you can work with it. In other words, if you look at part B, there's a lot more going on in that summation, and so we've got to really be on top of our algebra. So let's do it. Part B, we're going to take the limit as n approaches infinity of the absolute value. Let's change everything in this problem to an that has an n to an n plus 1. So we would have n plus 1 quantity squared times 2 to the n plus 1 plus 1, or n plus 2 power. All of that would be divided by 3 to the n plus 1. And then all of that would be over the original nth term expression. So there's our setup. Typically, that would also be our first point. Once again, I don't think that the absolute values are serving much of a purpose in this problem. So we can get rid of those and at the same time multiply by the reciprocal. So this numerator is still going to be an n plus 1 squared times 2 to the n plus 2, but he's going to be joined by the denominator here of the denominator, 3 to the n. And then let's keep tabs of what we have here in the new denominator, 3 to the n plus 1 times n squared times 2 to the n plus 1. Well, I don't know about you, but that's a pretty wicked looking limit. I think we better simplify this thing before we have any chances of potentially finding out its limit. So what we're going to do is notice that I'm going to highlight combinable or reducible terms. So these two in yellow, let's tackle those first. 2 to the n plus 2 divided by 2 to the n plus 1, subtract the exponents, and you've got yourself a 2 in the numerator. Let's look at, how about a different color so we don't get confused? How about these orange things? Those look like that they can be reduced. So 3 to the n over 3 to the n plus 1. Again, if you subtract the exponents, n minus the quantity n plus 1, you get a negative 1, 3 to the negative 1, which just means that the 3 is going to reside in the denominator. Now, the things that aren't highlighted, don't get too worked up about trying to reduce those, because A, you can't, and B, you don't really need to. Because if you write those alongside the 2 and the 3 respectively, you can see that the highest degreed n on top will be an n squared, the highest degreed on bottom will be an n squared, so you can just divide the exponents. 2 divided by 3 is your answer, which is less than 1. I probably could have written that over here just to kind of emphasize it's not a bad idea. And because we are less than 1, I know that once again, we will converge. So we're 2 for 2 on the convergence. All right. Now I want you to look at C because C is a very special problem. Perhaps you remember a while back, we talked about how n factorial can just beat up pretty much any kind of a constant raised to a power, even if that constant is a pretty large number. Basically, the larger that constant is, the more terms we'd have to go out before we can say that the factorial is going to be a larger. But what if that base is not a constant? So this is a really interesting problem because I think you guys understand that if you have a fraction where the numerator is just getting bigger faster than the denominator, then you know it's going to diverge. On the other hand, there's a pretty good chance that your summation is going to converge if the denominator is a lot bigger than the numerator. But sometimes we have something like this that's pretty tough to tell. And so that's what's so great about our good friend, the ratio test. The ratio test does an amazing job at working with factorials. So here we go. The n to the n is going to become n plus 1 to the n plus 1. Divide that by n factorial. And then all of this is divided by n to the n over n factorial. Oops, I already made a mistake. I didn't make this n factorial an nth plus 1 term. I got time to fix that. There we go. That's what I should have said. So hopefully that makes sense. That's your nth plus 1 term divided by your nth term. Well, once again, for the third straight problem, these absolute values absolutely mean nothing. So I'm going to get rid of them. And at the same time, I am going to rewrite this so that I am multiplying by the reciprocal. So here we go. Now, where do we go from here? This problem is really special. I love this problem. You may not like it, but I love this problem. So what do we have? Well, we've got the limit as n approaches infinity. Now we can cancel n factorial over n plus 1. When we do that, kind of like we did before in the previous problem, in part A, we have n plus 1. Now, if we take n plus 1 to the n plus 1, and we want to divide that by n to the n, well, there's a couple of things that we can do with that. The first thing that I might suggest is that you realize that you have an n plus 1 to the first in the bottom. You can actually combine this n plus 1 to the n plus 1 power with that n plus 1. But if that's a little tough for you to see, what I might suggest is we break apart n plus 1 to the n plus 1 by saying n plus 1 to the n times n plus 1 to the first. Notice whenever you have like bases, you would just add the exponents, and that's exactly what's going on here. Now, don't forget there's still an n to the n on bottom. I don't want to forget him. So basically, you can see that the n plus 1's cancel, and then you're left with something that may or may not look familiar. You're essentially left with, I'm going to highlight it here in blue, this numerator over this denominator. And if you notice, they both have a power of n, so I could write this as n plus 1 all over n raised to the n. Now, for my calculus BC students, this is going to mark the 4th time in your journey with calculus with me over the last almost 2 years that you have seen this limit expression. And it's a special definition of a very special number, e. And I would say at this point, you probably want to file this away. I think it's a good idea to know that, not so much for the AP Calc BC exam, but you never know when I might be so devious as to pull this out. And it's just a good thing that I want my students when they leave Avon High School to know, because the definition of E is a pretty powerful thing. All right, so you can certainly play around with this. You could graph this function and see what happens to the graph as x gets really big if you graph it as a continuous function of x. We've done that before with you, but like I said, it's been a while. So what do you know about E? Well, I'll tell you what you know about E. It's greater than 1, right? 2.7. So basically, you know that this series is going to diverge. In other words, I think it's quite possible that n factorial may have met his match, and that n to the n is likely to grow faster. Now, I suppose if you saw this problem standing alone in a multiple choice problem, and you saw that fact, you may not have to do any of this work if it's a multiple choice. So that's something to consider. And finally, we'll wrap things up with part D. We're going to take the limit as n approaches infinity of the absolute value. Now notice we have -1 to the n plus 1 times square root of n plus 1, all divided by n plus 1 plus 1, which is really an n plus 2, and then that placed on top of -1 to the n times the square root of n all over n plus 1. Lots going on there. Now, we are going to go ahead and think through a couple of steps ahead. If I have you just focus for the time being on these two terms, I want you to notice that you can divide them by subtracting the exponents. And doing so would give you -1 to the first power. That's the same as -1. Finally, the absolute values serve a purpose because they will wipe away that -1. And so at this step, I'm going to say, let's go ahead and remove the absolute values and then forget those two green statements ever existed. And then we just need to multiply. How about we get the right pen? That was funny. Let's go ahead and multiply by the reciprocal. So I have n plus 1 on top. That's going to be joined by n plus 1. So I have, the square root of n plus 1 on top joined by n plus 1. And then for the denominator, n plus 2 joined by the square root of n. So it's going to look a little something like that. Now, if you think about, oh goodness, I don't think we can do much more simplifying. And really we can't. This is a tough thing to simplify. What's going to happen here is that if you think about what is the leading coefficients exponent, just focusing on that alone, well, we've got an n to the first and an n to the 1/2 right there. So you could almost think of that as being an n to the 3/2 power. The same thing is happening in the denominator, n to the 3/2 power. So yes, it is true that this limit is 1. Now you're not going to like what you're about to see. What did we say the conclusion for the ratio test is if the limit is 1? The ratio test is inconclusive. Okay, so determine the convergence or divergence. I'm actually going to alter the directions here just a little bit for the purpose of the time in the video. We're going to stop and just say the ratio test is inconclusive. I know that's a bummer, isn't it? All of this work to not even be able to get an answer. Well, let's let this serve as a lesson. What kind of series was this to begin with? It was an alternating series. Maybe the ratio test isn't the best thing to use for alternating series, or at least ones that look like this. So in other words, we do have another test that we could certainly fall back on. And like I said, for the purpose of this video, I'm not going to go through that. You could do that as an exercise, and if you're one of my students, I can tell you in class whether or not your conclusions are right. But a question like this is best asked if it's going to conditionally converge, absolutely converge, or diverge because of the alternating component. Hopefully, this gives you a little taste of the ratio test. It does have quite a few steps that could also kind of result in having a lot of points for the problem. But I want to tell you, of all the tests that you're going to need moving into the very final part of Unit 10, our Unit 10B units set, the ratio test is going to stick around quite a bit. So keep practicing it. We'll see you the next video.